Sorry, I'm taking over for the next part of 212, and we've got 7 lectures, and there will be a workshop towards the end on reaction dynamics. What I want to do in this first lecture really is set the scene for what we're going to be looking at. Mainly we're going to be looking at the growth in experimental techniques which have led to our understanding of reaction. But we will have to pull in some theoretical models and some key understandings as we go through. So the first question really is, what is reaction dynamics? And reaction dynamics is what chemical kinetics has grown up to be. Chemical kinetics is almost largely, when you do kinetics in first year, second year, you essentially look at ways of getting a rate constant. And a rate constant is essentially a 19th century construct. Arrhenius was working back on the concepts of rate constants back in 1873. So then there's the whole of the 20th century, if you like, to try and proceed and get cleverer at this. And towards the sort of latter third of the 20th century, there were great strides made in experimental techniques, which meant we've been able to move on from rate constants. What I really want to do today is set the scene and get your mind working in the way in which we think of reaction dynamics, and to try and get a few key ideas in. Right, so it's a study of molecular collisions in chemistry. It's studying real collisions, and for that reason it took 100 to 150 years to get the techniques there, because we have to study individual real collisions, not average quantities as you would get if you were just studying things in a test tube. So this is why it's so difficult. And the gain, if you like, is to get a full understanding of what happens during reactive collisions. Oh, I should just point out, you've got on the handout, you've got the slides, you've got a few gaps to give you something to write in as we go through, so you've got something to colour in, so you don't get to see. On Blackboard, my version of the slides will be there in case you miss anything, so you'll get the full version on Blackboard. Give you something to do as we go through. So, how different is it from kinetics? Well, kinetics, you really just talk about a rate constant. And you're dealing with an incredibly averaged quantity. Instead, we're going to be looking at detailed information at the molecular level. So we're not going to talk about rate constants. We're going to use terms such as translational energy, orientation, vibrational distributions, angular momentum, trajectories. These are collisions. And so we're going to be looking at measurements and our understanding of collisions, real-time collisions in chemistry studied as individual collisions. We need to establish a link between kinetics and reaction dynamics, and that will be part of today's lecture as well, giving you a feel for the links. Okay, what I want to do now is to try and break what the organic chemists have probably driven into you for all the years you've been here, and we'll try and give you a proper picture of what a collision looks like. It's very great honestly doing everything in a nice concerted way. You need to look at the different motions involved. So first of all, I want to get a feel for what the time scale of molecular collisions are. And for this, we're going to look at gas phase collisions as being the simplest we can deal with. So imagine 2 molecules bumping each other in the gas phase. So the question is, how long does a collision last? What time scale are we going to need to be able to make our measurements on? Well, if you want to know how long it takes for something to occur, you find the collision distance and you divide by the velocity. What do I mean by a collision distance? Well, molecules bumping into each other are not billiard balls. They don't travel along and suddenly hit. Once they start to get close to each other, then there are interaction energies. So you get van der Waals interactions, you get chemical interactions. So they feel the presence, a molecule will feel the presence of another one when it gets close enough. So, and that's when the collision can be said to be starting. So what sort of distance are we involved with here? So really, what sort of distances do chemical forces, physical and chemical forces, operate over? At a typical van der Waals potential, molecules feel the van der Waals potential first. Chemical potentials are shorter range. And there's a typical van der Waals, coming down to 50 kilojoules per mole, thereabouts, something like that. There's about 7 or 8 angstroms. Chemical forces, the chemical interactions will be shorter. They're less than the van der Waals radii, of course. So chemical force is shorter range but much deeper. Perhaps a minimum 1.5, 2.5 angstroms. Typical bond lengths, 1.5, 2.5 angstroms. So really, we only need a rough feel. Let's just say 5 angstroms. Let's just say typical interaction distance is about 5 angstroms. When things get within 5 angstroms, they'll start to affect each other significantly. So we've got the top line of this. Collision distance is somewhere around about 5 angstroms. Much further away than that, they don't really detect each other. Okay. But if we want to do the second part of this calculation, we've got to divide by the velocity. So the question is, how fast do molecules go? So we're sitting in a room full of them at the moment, whizzing round. Anybody know how fast they go? So we calculate it. Pretty easy. If we're in a room at temperature T, there will be thermal energy proportional to kT, kBT. That's the proportionality constant that gives you the energy proportional to something being other than absolute zero. And if we're dealing with a gas, that's mainly going into kinetic energy, the molecules moving around, and that's what we're interested in here, the molecular velocity. So the kinetic energy is easy. Kinetic energy is 1/2 mv squared. And that kinetic energy has arrived from the thermal energy of the system. And the equipartition of energy tells us that there will be 1/2 kT, so that's the Boltzmann constant, that K. There'll be 1/2 kT in each degree of freedom. And there are 3 degrees of freedom in a room like this, X, Y, Z, 3D system. So there'll be 3/2 kT for the thermal energy, and it'll equal the kinetic energy 1/2 mv squared. That's a pretty trivial calculation. It's an average quantity. So now we can just solve for V. And we call it the root mean square velocity, RMS. And we do that because it turns out there are 3 measures of velocity that we'll make use of. And this is one of them. And it's the root because it's got a square root in it. And it's the mean because it's an average property. It's the kinetic energy and the average of the thermal energy. So it's the root mean square velocity. So it's pretty easy to now do some calculations. You just have to pick some molecules and some temperatures. So typical values. Right, what I've got there is molecule H2, HCl and chlorine. And we're going to work at 300 Kelvin, and here's what the velocities come out to be. 1934, 465, 326. Okay. What I've done here is I'm characterising the molecules. They're going to be important to us. The L means light, H means heavy. So that's a light-light diatomic. Both partners are light hydrogen. This is a light-heavy, light hydrogen, heavy chlorine. And finally, heavy-heavy, 2 chlorines. And we'll see different behaviour and different timescales when we've got light species mixed in with the heavy ones who are all light. Okay. So this is now the collision time. It's our 5 angstroms divided by this velocity. And obviously, the lighter they are, the faster they go. Because kinetic energy goes as 1/2 mv squared. If m is little, then the v has to be large. And so we find 0.36 picoseconds, 1.5 picoseconds, 2.4 picoseconds. So we're working in the picosecond domain. That's going to be our fundamental time scale for collision, picosecond time scale. So here we're down at 1/3 of a picosecond because we've got a very light species, but otherwise we're around about 1, 2, 3, 4 picoseconds. If we're going to do direct probing of a collision, that means we've got to do our measurements in 10 to the minus 12 of a second normally. That's pretty tough. So we'll find ways in which we can get around that to a certain extent. Okay, that's the first part of the collision. The actual collision, the time these two molecules experience each other as they come together. Right. What I want to do is to look at how many vibrations we get during a collision. Because this is perhaps where your mental picture of the collision does not correspond to reality. How fast do things vibrate? How many vibrations do you get during that collision we've just looked at? Well, we're dealing with diatomics. There's the vibrational frequency of the diatomic. So, that's the first year spectroscopy. Mu there because 1 over 2 pi square root k over mu. K is the force constant, mu is the reduced mass. Just remind yourself m1, m2 over m1 plus m2. So this is just very first year and second year that you've met those. And the time for a vibration, a single vibration, is 1 over the frequency. If it's vibrating 100 times a second, it's 1/100th of a second for the vibrational time constant. And we know the masses and we know the force constants from the infrared spectra, so we can calculate these for our three molecules again. So H2, HCl, Cl2. These are the force constants. 509 newtons per metre, 478, 320. This gives the vibration frequency in hertz, or seconds to the minus 1. And then 1 over this number is going to be the time it takes for a vibration. 8 times 10 to the minus 15, 8.3 times 10 to the minus 15, 6 times 10 to the minus 14. That 10 to the 14 times, so if we look at the vibrational frequency, 10 to the 14, 10 to the 13. Light things, remember this has got hydrogen and that's got a hydrogen. Light things vibrate very quickly. So either two hydrogens against each other, or a hydrogen just really vibrates against the chlorine in HCl. You can almost imagine the chlorine not really taking that much part in it. It's a hydrogen going back and forth. And they vibrate very quickly. Virtually all of the molecules are going to be around about 10 to the 13 hertz. But if you've got hydrogens in there, it'll be faster. But we can see 6 times 10 to the minus 14 of a second. It's much shorter than the time of the collision. So we'll come back to that in a moment. Okay. But what it does tell us already is that as the two molecules approach each other, they are vibrating a lot of times, even during that little collision. So if you see like an SN1 reaction or something, and they draw this sort of atom coming up, and the methyl iodide and the iodine goes out, and it looks like it's a simple transfer of the methyl group. The methyls are vibrating like mad during this whole process. We'll look at that again in a moment. So the time scales for vibrations are very much shorter. How about rotations? If you've got an atom coming up to a molecule, two molecules coming up to each other, they rotate. And this can play a big part in the dynamics. So if you've got an atom coming up towards the molecule that's rotating, it may rotate into an orientation where it won't react. And how fast does it rotate? Does it rotate many times during a collision? Does it rotate, a fractional bit during a collision? Well, this is where we've got to get this picture in our mind of what a real chemistry collision looks like. So how fast do things rotate? Well, again, just using diatomics, that's a rigid rotor. The energy of the rotor is Bj to J plus 1, where B is the rotational constant. It's not an easy question to ask, how fast does a molecule rotate in quantum theory? But what we can do is give the same amount of energy to a classical diatomic and see how fast it would rotate. And it'll give us a reasonable feel. The angular momentum will be the same, as we'll see. So this would be a classical version of a rotating diatomic. It's a half I omega squared is the kinetic energy. this would be like a half mv squared for translational energy, half I omega squared for rotational energy. Omega is the rotational velocity, and I is the moment of inertia. So I is mu r squared. So if you go back to again to your first and second year spectroscopy. Okay, the problem is, what value of J are we going to put in here to calculate the rotational energy? And this bit is for those who are just really, well, we're going to make use of the result. I'm going to tell you how you get it, but I'm not expecting you to be able to do it. This is actually the probability, the Boltzmann distribution for the populations of J levels. It's 2J plus 1 e to the minus bj to j plus 1 over kt. If you want to find the peak of this, you would have to differentiate it with respect to J, set it equal to 0, and find the maximum. So, those of you who are very interested can go away and do it, but that's the answer. So, you solve it by doing dp of j by dj equals 0, finding the maximum, and you would find that j max equals kb t over 2b. So now we've got the value of j we should use. We'll use the peak j distribution. As I say, it's a slightly difficult question because you get a range of j values populated. So you've just got to, so we'll just pick in the biggest one. That's the average, if you like. Okay, so we've got J max, we've got a value there. We can put J max back in here, we've got the energy, and then when the energy we can calculate to half I omega squared. So we've got half I omega squared, you can see J max into J max plus 1. If J max is much greater than 1, let's just forget the 1 and we'll call it Bj max squared. That makes life easy because we just square the square root sign we had, and we get half kt. A little bit of fudging, but good enough. Half kt. So that's the amount of energy that we've got. And so now we can calculate the omega value. Omega is just kt over I. The halves have cancelled both sides, a half there and a half there. So we've just got the omega equals kt over I square rooted. This is going to be in radians per second, because it's an angular rotation. So we need to divide by 2 pi to get in rotations per second, because there are 2 pi radians in a circle. And of course the time for a rotational period is 1 over the rotational frequency. So it's going to be that upside down. It's going to be 2 pi square root I over kt. Okay, so slightly longer to get at rotations. That's because really we've got a spread in rotational levels, so we have to think a little bit more carefully about how we do that. Right, there's our 3 molecules again. Here's the moment of inertia. The moment of inertia, 10 to minus 48, 10 to minus 47, 10 to the minus 45. This is much more like the sorts of numbers you see. Moments of inertia with hydrogens on, very small, because they don't weigh very much, so they can rotate quite quickly. Don't have much moment of inertia. Equally, J max is actually not very large when you've got hydrogens on. Turns out your rotational levels are inversely proportional to the moment of inertia, which means they're very largely spaced for things with hydrogen in. You can populate it. If you've got very heavy things, you get all the levels are very close together, and you populate a huge number of them. So J max 1, J max 3, J max 70 is something when you go to CO2. So you populate an awful lot of levels unless you've got an hydrogen stuck on there. Right, there's the frequency, there's the time period. 1.9 times 10 to the minus 13, 4.5 times 10 to the minus 13, 3 times 10 to the minus 12. 3 picoseconds, half a picosecond, down here at 0.2 of a picosecond. But we're back in the picosecond regime just about. And for largish molecules, a few picoseconds. Okay, but that's about the same time as the collision was. So now we've got a picture. Things come together, like that, and they're rotating at a similar-ish speed. So they don't rotate lots of times, and they don't rotate only a little tiny bit. Their rotational period is likely to be similar to the time period of the collision. So sometimes it might not be a full rotation, sometimes it might be a couple of rotations, but it's not so different. But the vibrations are very, very much faster. Things vibrate. And this is important to us, because the way molecules shuffle energy around is by vibrations. This allows us to shuffle energy around complexes and transition states. So this tells us that we can get a lot of energy exchange occurring. So what I wanted to do is finish off with this bit, is to have a look at relative time scales. So this is it. Light species have small eyes, so large rotation spaces. Okay, comparison of time scales. This is the collision time divided by the rotation time. 1.9, 3.3, 0.7. So 1.9 rotations during the collision, 3 rotations during the collision, 0.7 of a rotation during the collision. That's what we said. Similar time scales for rotations and collision time scales. So they're pretty similar. So if we do the same calculation with the vibrations, however, 45, 180, 40. So a lot of vibrations during that collision. And for the same reason, if we do the rotation divided by the vibration, 24, 54, 57. So as things rotate, they are vibrating many, 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 many times per rotation. Every rotation has got a lot of vibrations in it. 20, 24, 57. Like that. So now we've got a picture of the concerted motion of species. A relative speed of coming together versus their rotational speed versus their vibrations, and how they are relative to each one. So, got a picture now. Okay, so we do actually have the numbers. Right, so I want to really, for the rest of the lecture course, you should think those sorts of time scales. That's what the motions are doing. And those will have very significant impacts on the dynamics. Okay, this is actually the closest I ever come to organic chemistry. This is a piece of gas phase SN1 reaction that actually was discovered 2008 now. This is Cl- coming up to methyl iodide. This has been studied by molecular beam scattering. We're going to find out what that is. So it was all done in the gas phase, no solutions going on here. And then from all the scattering information, the laser probing little pictures of what is happening. So that's a sort of traditional SN1 reaction, which they were able to discover, but of course they were able to probe all the vibrational motions going on in the methyl iodide, probe the vibrational energy which ends up in the methyl chloride, and so on. But they also discovered another pathway. Which hits the molecule on the side, the molecule rotates around, puts apart and goes off. And they're able to show that this was actually, although not the major pathway, a significant pathway in the reactions. And this is the level at which we are going to be discussing molecular collisions, molecular dynamics. That is, we can get information on this sort of level of behaviour that's going on. Okay. I need to introduce you to a very important concept. The impact parameter. When things bump into each other, they very hardly ever bump into each other right down the line of centres of the two molecules. It's quite likely that if you were to draw the direction of this one and the direction of that one and the middle of that one and the middle of that one, there would be an offset. And we call that offset the impact parameter and we give it the symbol B. And we're going to make huge use of the impact parameter in lots and lots of our models for reaction dynamics and so on. So I need to just introduce the term at this point. The impact parameter is, if you like, how far they were going to miss each other centre to centre. Obviously, if this gets too large, they do miss each other. But for shortish values, that will hit part of that. And that second collision that we just saw was something with a significant impact parameter because the chlorine hit the sort of edge of the methyl group. Okay, so quite often, and you saw it in that one, there is a point at which one of the atoms transfers between one molecule and the other, and it will go through a complex or transition state. And so we're going to make use of the idea of a complex or a transition state. The transition state may be essentially a single point, or it may be actually a quasi-bound system which lives for some finite period, perhaps a few rotations. So we will look at the way in which we characterise the transition state. But again, we get a complex, an intermediate complex, which may just last for half the vibrational period. It may last for quite a lot more, in which case we can expect to get energy redistribution occurring. Right. What I need to do is to get us thinking, if you like, in a much more detailed way than rate constants, but I want to tie into rate constants because that's what we know from reaction, from kinetics. So let's just think of that reaction. A plus B goes through a complex, makes C plus D. And initially, we'll have quantum states here and quantum states there. Finally, we'll have quantum states, and we'll have a complex with quantum states. And they're coming together with some translational energy E. What I'm going to do is just frighten you a bit, and then we'll step back from it. If you want to do quantum calculations of molecular collisions, let me just take you through what you've got to consider. You've got to consider initial quantum states here. You've got to consider on this side final quantum states. You've got to consider the energetics and orientation of the intermediate complex. Collisions will occur at some impact parameter. B, they'll be in a plane. We'll look at how we know they're in a plane. It's through angular momentum conservation. Beta. Reaction products C and D in their own quantum states, K and I, will scatter away at angles theta and phi. When you do billiards and you hit things, if they have an impact parameter that they're not head on, then they'll scatter off in different directions. If you're doing it in 3 directions, 2 angles, they scatter off. So these would be the 2 angles in 3D space that they would scatter off at in quantum states of the products. And this complex would have to be characterised by an energy state, K. So we would have to calculate a quantity for an individual collision, which is the probability of going from initial state I, initial state J, to final state K, final state L, at a certain kinetic energy with an impact parameter in a particular plane, scattering into 2 angles and a quantum state K for the complex. So if you're doing quantum scattering for collisions, that's what you have to calculate. It's a big job. What I want to do is go from here to the rate constant. And it's not something I expect you to be able to reproduce, but I want you to now feel, if you like, this is all the information that's available on a collision in principle. And we've been measuring for the last 100 years rate constant. So let's have a look at all the information which we lose. And we'll pull in where we've got to nowadays, show you where we can start getting the information. Right, well this is too much. We can't measure these. What can we measure? There we are, we're starting off with our frightening amount of information. We generally can't probe the complex, so we'll integrate overall, we can sum over all the states of the complex and get rid of this K quantum number. Now, on the very back page of this, there's a horrible big diagram with lots of arrows. Could be. Oh yeah, there you go, on the left-hand side. I'm going to work through that diagram. I would never expect you to reproduce that diagram. It's there simply for the moment. I'm just going to work through how we lose information and where we can start to get some of it back. We can't control the impact parameter. We can't control how closely molecules are when they bump into each other. They just go off and bump in at some impact parameter. We can't fire molecules and can't quite do billiards with them and decide just to take a glancing collision off from one molecule off another. So I'll have a range of these, and the same with the planes which will occupy. So we need to integrate over there, in which case we lose two variables here, beta and B. Still can't measure those. So we have to, in this case, integrate over the B and beta, or in this case, get rid of the K again. We're losing information all the way, it's dreadful. But here we are. This is called a differential cross-section. It's the intensity of collisions going from quantum state I and quantum state J, initially, to quantum states K and L, finally, as a function of the translational energy and the two angles in space that they're scattered through. That's actually measurable. We will come to the end at where we've got to systems that have done that, but it's very, very, very hard to do that. You are measuring 1, 2, 3, 4, 5, 6, 7 parameters in the collision. But that's the first of our measurable quantities, differential cross-section. In principle, it's measurable. We can probe initial and final states using lasers and things like that. We can control the translation energy. We can have detectors that move in space to measure the angles in space for the collisions. So we can do this. Okay. First of our measurable quantities. Right, so there it is, that's the first of our measure one. We hardly ever do experiments that measure all of those. We've got to throw away more information to get down to do experiments that we can normally do. So it might be that we can't control the initial quantum states. We just get the Maxwell-Boltzmann mess of initial quantum states. So we have to sum over all the initial quantum states. We don't have control of it. But that we could probe the product states using laser-induced fluorescence or something like that. We're looking at, we can probe the product states. And we can do it as a function of the translational energy, and we have detectors that probe in space so we can find out where they're going, find the angles. Or it might be here that we can't measure the final quantum states, but we can control the initial quantum states. We'll look at techniques where you can select initial quantum states, either using laser techniques or using hexapole electric fields and things. Or it might be that we can't control the initial quantum states or detect the final quantum states, but that we can do it as a function of the translation energy and the angles. That's cross-beam molecular scattering. So 3 different differential cross-sections. So that's lost some information, that's lost some information, that's lost those 2 lots of initial information. That's still an enormous amount of information. Gets you the Nobel Prize if you do it first. Right. If you don't have detectors that can scan around space and measure these quantities as a function of angles, you just have to throw away the angle. Essentially, you're summing over all the angles. So it might be you're just probing a bulk gas with a laser. Very fast at probing it. Okay, so now we get cross-sections, we're called total cross-sections. And it still could be state to state, could involve just the final states, could involve just the initial states. Might be that you don't know the initial states, you just know the cross-section as a function of the energy. These are all very doable experiments. These are differential, these are now called total cross-sections. These are actually very doable experiments. Probably for the last 25, 30 years, these have not been that difficult to do. We're going to look at some data in a moment. So there they are again, the total cross-sections. If you've got a gas like this room, it doesn't have one energy, translation energy. It's got a range of velocities. It's got the Maxwell-Boltzmann distribution of velocities. Therefore, it's got a distribution of energies. You've got some fast molecules, some slow ones. Big kinetic energy, small kinetic energy. So you should integrate over the translational energy distribution, which is the Maxwell-Boltzmann distribution. And now we get detailed specific rate constants. If we've kept the quantum states, we might have rate constants that involve quantum states. And if we sum over all those, we finally get the rate constant. So for the last 100 years, that's what we've measured. And all of that lot going right up there now on that last page is all the information that we've thrown away. So we haven't been doing that well by measuring rate constants. They are almost information free. So what we're going to do in the course is we're going to look now at working our way to different areas of this and selecting some of these cross-sections, differential cross-sections, and looking at techniques that make use of that. Now, I'm never going to ask you to reproduce that diagram. Don't try and learn it or something. On Blackboard, you'll find you've got the handouts on the Blackboard, you've got the lecture notes, and you have some bits which are labelled non-examinable. And you'll find this is in the non-examinable section. So when you come to revise, you look in the non-examinable folder and make sure you know which ones are in there. So that means I'm not going to ask them. Right, so that's it. There's that picture where we start off with the quantum collision, we end up with the rate constant. And what we've got is a tremendous loss of information as we come down through there. And so what I'm going to do is start looking, in some ways working our way backward through here to try and get as far back up that ladder as we can. Right. I keep using the word cross-sections. We're going to have to define what cross-sections are a bit more fully. But I want to show you at the moment as well, just working back a little bit back through that diagram to get rate constants that involve quantum measurements. So let's just think of the traditional kinetic measurement. A plus BC goes to AB plus C, rate equals K times A times BC, and also there's a temperature dependence to the rate constant. So that's Arrhenius, that's the law of mass action. And that's what kinetics has been for you so far. But certainly for the last 30 to 40 years we've been able to do state-resolved kinetics. That is, we can determine the vibrational populations, perhaps of BC and perhaps of AB, sometimes both, sometimes only one. Then we can measure the state-to-state reaction. So for instance, it could be A plus BC in some initial vibrational state, going to AB in some final vibrational state. And we're measuring the vibrational state of this and the vibrational state of that. Or we're controlling the vibrational state of this and measuring the vibrational state of that. And what we want to know is, so now we have a rate constant, but it goes from state I to state M. So it goes from I to M. So we have a rate constant which takes us from one particular initial vibrational state to one particular final vibrational state. What I want to do is just to see how these rate constants are related to KT. How are they related to the thermal one that you get? Because there's one little tricky thing in there. Let's just look at some examples. Here's barium plus HX, where X is the halide. So fluorine, chlorine, bromine, iodine. And making barium halide. And this has been probed by laser-induced fluorescence. So we can measure the populations of the vibrational levels of the barium halide. So these were done by Dick Zare. Indeed, some of these experiments were done by Chris Whitehead a very long time ago when he was a postdoc in Dick Zare's group in Columbia. So, before he became head of school by some long time. So, and he was involved in the development of a lot of laser-induced fluorescence measurements in quantum scattering. Right, so barium plus HF, these are the vibrational levels. There is HCl, HBr, HI. As things get heavier, vibrational spacings get closer. Vibrational frequency is 1 over mu, the reduced mass. So a lot more levels here. The important thing actually is these levels peak quite a long way from zero. This is a big surprise. This is a shock. Well, it's not, but it ought to be for you in the sense that if you calculate vibrational populations, you would say, of course, that they would just fall exponentially because that's the Boltzmann distribution of vibrational population levels. The Boltzmann formula for vibrations is e to the minus ev over minus e naught over kt. Again in a moment. Vibrational populations just fall off. These don't. They grow and then drop down. That means this molecule that's been created, and it's not in thermal equilibrium. And this means that the reaction has gone so fast that energy has not had time to equilibrate. It doesn't have a temperature. Well, it certainly doesn't have a temperature because the temperature it would have a falling Boltzmann population. This is a non-equilibrium system that's been created during this collision. And this gives it away because it's what's called an inverted population. Right. So they're all inverted populations, they're not in thermal equilibrium. That's the Boltzmann law for simple vibrations, diatomic, Ni equals n naught e to the minus ev over kt, that is just the falling exponential. So these levels should just drop exponentially. If you didn't measure quickly enough, and these things start bumping into other molecules, there'll be a Boltzmann population within 2 or 3 collisions. Energy will redistribute very rapidly. Right. Here's another version, but this time we're actually going to control the initial quantum state and measure the final quantum state. We can control the HF quantum state here using an HF laser. What the Americans spent a long time developing HF chemical lasers to shoot down missiles. Didn't really come to anything, but they did learn how to make good HF lasers. So you can actually take HF in its ground state, which you would have normally coming out of a gas bottle, hit it with an HF laser, put it up into V equals 1, and then do a reaction with it, all your molecules up in V equals 1. So controlling your quantum state here, and then measuring the barium fluoride quantum states. Here it is at low translational energy going for V equals 0. That's a Boltzmann type population. Not quite, but it's there. This is going up to V equals 1. That's 7 kilojoules per mole. It's an inverted population. We can put a lot more translational energy in, but go back to V equals 0, and we've still got a Boltzmann type population. So the dynamics has changed massively by going into V equals 1. And it's not a function of how much translational energy we've got in the collision. The collision dynamics are being affected by the energy, in this case, going into vibration. And the dynamics is entirely different when you're in the first excited vibrational state from when you're in the ground vibrational state. So only 7 kilojoules per mole there, 7 kilojoules per mole there. Big difference when we put one quantum in the vibration. We can stick loads more energy in the translation. Doesn't affect it. Looks just like this one, except it goes out. There's the maximum energy, that's the maximum energy. It looks pretty much the same, just goes out to the maximum energy. So we're going to have to look at why it is that energy going into particular forms affects the dynamics that you see. Right. Write a relationship down here now. We've got A plus B, C goes to AB plus C. But we're looking at the fact we could be going from this quantum state to that one, that one, that one, that one, or that one. We could be going from that quantum state to that one, that one, that one, that one, that one. In other words, we're going from 0 to any quantum state M on this side, or here we're going from 3 to any quantum state M on that side. So we've got a whole range of quantum states that are initial and final. So the rate, I've just picked one out in red, the rate going from initial quantum state I to final quantum state M is K I M A times. And now it's not the concentration of BC, it's the concentration of BC in my initial quantum state. So it's slightly different because if I'm doing quantum state to quantum state, it's the concentration in that initial quantum state which is important, because that's the one that's taking part in my collision that I'm considering. I'm just going to write that in a different way. The concentration of BC in initial state I is the total concentration multiplied by the fraction in state I. So 20% are in state I, it's 20% of the total. If 5% are in state I, it's 5% of the total. That's just a slightly different way of writing that, but in fact normally we can calculate that if our reagents are in thermal equilibrium. It's just the Boltzmann population. So that suddenly lets us write it in a way that we can calculate the Boltzmann population. So we can now just put that into there, collect the terms. Rate from I to m equals the population in state I times the rate constant linking the two states times A times BC. So that looks a bit just, that's the normal kinetics term we've got, A times BC. So the only time I'm going to go through this level of detail with you. Right, what's a state going from I to all final product states? Supposing we don't measure the product states, we just know we're starting off at some initial quantum state, we go to any final quantum state. Then we'd have to sum over the quantum states, the final quantum states. And we just call that a rate constant now for the initial quantum state. We've lost the final quantum states because we've summed over them all. So now we've got a relationship to calculate to show how we go from these rate state-to-state ones to one that involves just the initial state. And finally, if we summed over all the initial reagent states, so this is ordinary chemistry now, we just mix the two things together. We'd have to sum over both the initial states and the final states, and that will finally give us the kinetics that we saw. So here's the rate constant again. This is our rate constant you'd go and measure. It involves the initial states, the final states, state-to-state rate constants, and populations. That's the killer. You can't just take a list of rate constants and add them all up. You have to know the populations in the levels as well. Okay, I'm not going to do any more of that. We're never going to come back to this. But I wanted you to get a feel for just even going from state-to-state rate constant to a final rate constant. You do all of that averaging, which is sacrificing all of that information. So this is why we shan't be looking at final rate constants again. We are going to be looking at state-to-state stuff. Right. It looks even worse because if you put rotations in, because you'll get another double summation, one for each rotational state, which we find. Right, but you can do it. For instance, that's some old data, but it's hydrogen plus thionyl chloride goes to HCl. And this has been measured in both the V quantum state and the J quantum state. So these are different V states and these are the J populations. So all of that information is actually quite doable. We have quite old data there. It's all quite doable. I won't even go into this. This is drawing contour plots of vibrations and rotations, energies for a system like that. Not going to look in detail in those. But just to give you a feel, that information has been available for a long time. The fact that we can probe products in vibrations and rotational quantum states. But I just want to remind you a couple of things about the Boltzmann population in the last 2 minutes. Just so you read a little bit, remind yourself of the Boltzmann population expression. We are going to make use of it throughout. Mr. Boltzmann solved the problem of if you've got a series of quantum states at temperature T, how does the population change amongst levels? And I hope you all remember it because he got very depressed that nobody could remember his formula and committed suicide by drowning himself. And it's probably because he had second-year tutorials in which nobody could remember the Boltzmann formula. So we try and remember the Boltzmann formula. So it tells us that the number of molecules in state I over the number in state 0 will go as e to the minus ei minus e0 over kt. And if there's degeneracy involved, there's the degeneracy of level I over the degeneracy of level 0. So this is your stat mechanics. The Boltzmann population, Ni is the number in level I, Gi is the degeneracy of level I. So, and normally, and what we actually want is those little fractional populations. So the fractional population is the number in level I over the total number, and the total number is just the partition function Q. And all the fractional populations come to 1. So if we were going to calculate them, that's what we do. That's stat mechanics. I'm not going to do stat mechanics with you. Just remind you though, you've done stat mechanics. Then last semester, I think, is that right? That's all right. Right. So just fractional population to Boltzmann population. But we're going to keep pulling in on that. So let's just look at it applied. If you're applying it to vibrations, this is the diatomic. EV equals V plus a half, EV minus E naught equals V plus a half, H nu minus a half H nu, so it's just VH nu, NV over N naught, there's no degeneracies, e to the minus VH nu over KT. There it is for oxygen at 1,000 degrees Kelvin. Nearly everything in level 0, small percentage in level 1, virtually nothing in level in level 2 and so on. Here it is falling away exponentially very rapidly. So vibrations, most things down in the ground vibrational state. Not too much in the high. I've gone to 1,000 rather than 300 because I can't really see that at 300. Okay. For rotations, calculation we've done, EJ equals BJ to J plus 1. They're degenerate though. Each J level is 2J plus 1 degenerate, so we need to put the degeneracy in as EJ minus E naught. So we get NJ over N naught equals 2J plus 1 e to the minus B, J to J plus 1 over KT. And if you plot that at 300, that's oxygen at 300 Kelvin. That's your rotational populations. And you can see we're up to level 20, we're peaking up somewhere around about level 10 here. So rotations are different. Rotation levels are much closer together. They all get quite a bit more of the Boltzmann population, and they're weighted by this degeneracy term. So we've got the, there it is, 2J plus 1 degeneracy term. And so what you've really got is the exponential term is dropping things away, the 2J plus 1 term is growing in. So it goes up first, and then the exponential wins, and it falls back again. So we are going to pull in. I'm just going to assume that you understand what I mean if I talk about a Boltzmann population now. So most of that, in many ways, has been things you already knew. So from first year, second year kinetics, spectroscopy, and a little bit of stat mechanics. So next lecture, we actually will start in on modern reactor ionics.